Okay, so it's about to start. So I will kick off this session of several demos, and the first one is called RISC-V as an enabler of heterogeneous compute. My name is Zdenek. I'm CTO at Codasip, and in upcoming 10 minutes, I will show you our technology and how actually part of it, to be more precise, compiler, can help or is part of the heterogeneous compute. So if you look at the agenda, I will have like first couple of minutes dedicated to the introduction of our company and the technology itself. I'll be rather quick in this case, and then we will spend the most of the time doing the demo itself. I will try to code something and show you the results as the time goes. So let's start with the company overview. So for those of you who doesn't know Codasip, so Codasip was founded back in 2014. But since then we grew significantly. So right now we have more than 250 people. We have design centers across Europe, and the main focus is on RISC-V CPUs, of course, because we provide RISC-V IPs. But not only that, we provide also the tools by which you can customize them, which is then the enabler for the heterogeneous compute. So you may ask a question why we even talk about that. The reason for this one, there are actually a couple of reasons for this one. So if you look at the industry, so the things that were driving semiconductor economics, kind of falling apart. So things like Drell scaling, Camden's law, or even Moore's law, depending whether you believe in that or not, stop scaling, and therefore we need to look at the other techniques or other technologies, how we can boost the performance, how we can get to the point where we need to be. There are a couple of approaches that we can look at. We can maybe look at the new technologies, new technology nodes, but this is not a kind of economical viable as much as we would like to have, so we need to kind of look at the other things. One could be maybe optics, maybe carbon nanotubes, these sort of things. These are really fancy stuff, but maybe not mature enough as of today to be deployed widely. And therefore, we think that the right approach as of today is through the heterogeneous compute, where we tune individual parts of the design according to needs or desires. So then actually you came up with the architecture or products that can get us to the point where we need to be in terms of the performance, power, and whatsoever. And this is what Codasip is believe in, and also provides tools and IPs that kind of help you with that approach. So if you look at the solution and tools that you will see in upcoming minutes, is that we will start with RISC-V IP, which is one of the Codasip RISC-V IPs. In fact, Codasip has a wide range of IPs, from embedded ones up to the application class CPU in the multi-core cluster. So we're going to use one of the cores that we have, and I will have a dedicated slide on this one. Then once we have this IP that is described in the high-level description language, which is the enabler for really fast design space exploration, we can give it to the tooling. Tooling then generates plenty of things, starting from the compilation toolchain. We are LLVM house, so we provide the LLVM compiler. That's the nice thing about the compiler, and we will see that in the demo, is that the compiler is aware of every single instruction, including a new one, and it's able to use this instruction automatically. But the compiler is, of course, not the only tool that the studio provides. It also generates executable models. It produces things like profilers, debuggers, and so on the SDK side. And then you can also enjoy the fact that you can get the RTL that's aware of the new instruction as well. Then you can implement that in whatever technology or FPGA you want. You also get a bunch of test benches or verification tools in general that then you can deploy in your verification strategy according to your desires. Speaking of the RISC-V IPs that we're going to start with, the thing that I like to mention is that they are fully verified, which means that those are not just an examples or templates. It wouldn't be good enough. In our case, these are really full-blown CPUs. You can even take them as they are, and you can put them into the silicon without no problem, because they are really high quality. And this is really important to realize, because then the starting point is robust, the foundation is really there, and you can take it from there. And we will do that. We will do exactly that with the with the examples. Speaking of the examples, I'm going to use the L31 embedded core, which is one of our embedded CPUs, fully compliant with RISC-V standards. It's highly configurable. What I mean by that is that you can enable or disable certain feature set, and no matter which combination you're going to choose, it's verified, so you can rely on that. But besides the configuration, which is a nice thing, it also enables you to do customization. Now, the difference between those two in the Codasip world is, once again, the configuration is something that the Codasip prepared, while customization is something that you can do on top of that. So what we're going to do is customization, in fact, and I will just switch to the studio itself, and we will go through a couple of examples. I hope that you can see that, right? So what I have as of today is I have like two applications. I have a FYR filter, which is just a filter that you are kind of familiar with. I hope that you can see that at least to some extent. And what we would like to do is to see where we are in terms of the profiling. So what I'm going to do is I'm just going to run the profiling tool and see where we are as a starting point. If I do that, I'm going to get a nice result where I can see the total number of clock cycles, which is in this case 17K. But not only that, I can also go and I can have nice annotation in the editor where if I move a mouse pointer to certain lines, I can see the disassembly view. And in this case, it's quite obvious that what I can do is actually add a multiply and accumulate instruction. Because it's kind of obvious that this would help in the code size, but also in the performance. So what I'm going to do is I'm going to just add few lines of code into the model of the CPU in the high-level description language called Codal, and we're going to just rerun the application to see the result. So this is actually the real-life example of the multiple accumulate. The code over here, which you can see is not that long, it's few lines of code. What we're going to do is we're going to have the make operation that we're going to have multiple operands, in this case like 3 source operands, 1 destination operand. We're going to read the register operands from the register file, so nothing really crazy. And in this case, we're going to do the multiple and accumulate and then write the results back. In this case, I'm not really into the timing necessarily. I'm just going to say, okay, I need just 1 cycle for this one because it's within my budget and I'm okay with that. Then what I can do right now is I can regenerate the SDK, which I already did, and I can recompile that and reprofile that to see where we are. So the changing of the SDK is quite simple. I'm going to just change the SDK to the new one. And if I do that, I can recompile the binary. And the next step would be to do the profiling with the new toolchain. So I have it, and I can see that the clock cycle was reduced by 2K. Well, if I go back to the C code again and move my pointer over here, I can see another hints that profiling tells me, which is, hey, we can add maybe post and pre-increment for the loads and stores because those are repeated over time again. So what I can do is, indeed, I can add this instruction to the CPU as well. And if you look at the number of lines of code, is again roughly about 20 lines of the code. So nothing really big, which is over here. So what I'm going to do is I'm going to add a new load and store with the post and pre-increments. Nothing significantly different. And I'm going to read the address. I'm going to use the load store unit that's already there. I don't have to reinvent the wheel. And the only difference from the standard load is that I'm going to write the increment. So again, I prepared the SDK already. So what I'm going to do is I can just simply change the SDK to the new one, which is over here. Recompile the app again. And rerun the profiling again. Which is quite quick, and I can see that I dropped down another clock cycles. And if I go back to the C code, I can easily see that my loads with post increments are recognized and used as we would expect. So I think that what is important to say here as well is that I haven't touched the C code at all. So everything is done by the compiler under the hood. I can rely on that because the compiler is good enough to handle all of that. Last example, because the time is running, so the last thing I'd like to show is the another type of instruction, so say a bit reverse instruction. I have some benchmarks, it doesn't really matter. What I'd like to point out is that we have functions over here or over there that computes the bit reverse operations that you can find in some DSP operations. And the point I'd like to mention here is that actually the compiler, if you add the reverse instruction, the compiler is smart enough to pick these instructions as well, even though the code is quite complex. You can see for loops in there, but the compiler is smart enough to find it out anyhow. So if speaking of the bit reverse, the instruction is really simple as well. So if you look at the description, it's just these lines of code, nothing really significant. You just read the operand from the register file, do the bit reverse, and write the result back. So if I do the standard compilation and the standard runtime, then we will have some basic results, and then really quickly do the optimization run. So this is the starting point, it's 40K of lines of code. What I can do right now is use the new instruction as well. So I'm going to do this. I'm going to switch to the new instruction, which is this guy over here, and recompile. And what I'd like to show you is that, in fact, we really have the bit reverse operation. So you can see over here, this is disassembly, and in the disassembly you can see that the compiler is smart enough to find even complex C code patterns and replace them with this simple instruction. And then the last bit is, of course, I can run it, and if I do, then I will see a significant improvement. So instead of the 40K, I have a 3K. It shows that even stupid simple instruction like bit reverse can really significantly help. Which leads to the final slide really quickly. I think that since we need to look for the new patterns, new ways how we can improve performance, power, whatever, the heterogeneous compute is really indeed a nice way to go. RISC-V is really, really well positioned for that. And with the tooling that the Codasip provides, you can be really, really good at what you need to do in terms of the heterogeneous compute, custom compute, and we can achieve really, really nice results in the end of the day. Thank you.